in the previous video, we looked at the definitions of the two specific heats, in particular the specific heat at constant volume and the specific heat at constant pressure. We saw how they are defined, and then we also saw how we could simplify that definition in particular cases. In particular, we saw how we could simplify it if the substance that we are working with is an ideal gas. We also saw how we could simplify it if the process that we are working with is either an isothermal process or a constant volume process or a constant pressure process, right? And so, in this video, we are going to look at a little bit more detail about how specific heats vary for ideal gases. And so, we will focus on ideal gases in this video, right? So, recall that the definition of CV is the partial U with respect to temperature at constant volume, and recall that this is always true. Well, it better be true because that's the definition, right? And Cp similarly is the partial H with respect to T at constant pressure, right? And for ideal gases, we have seen that U is just a function of temperature and H is also a function of temperature. And I would like to emphasize that this is not always true. This is true only for ideal gases, right? And so therefore, we can write Cv as du dt or du equals Cv dt, and similarly Cp equals dh dt or dh equals Cp dt, right? Although we have gotten rid of the partial differential, we now have a simple differential, right? We still need integration to evaluate delta U or delta H, right? And so, delta U will be equal to integral over the process Cv dt, right? And delta H equals integral over the process Cp dt, right? And as you can imagine, it's not always easy to perform this integration. As we will see in this course, we will work with computerized tools, and those tools make it very easy to evaluate these integrals, and in fact it's already done for you. So you can get properties directly from these computer tools. But before we had computer tools, we have property tables, and it's not always easy, or rather it's cumbersome to evaluate this integral. So in some special cases, we might be able to pull this Cv out of the integral or the Cp out of the integral, right? And if we can do that, we just become Cv times delta T, right? Or Cp times delta T, right? So in some cases, we could get away with getting the Cv or the Cp out of the integral, but we must know what are the limits and what are the kinds of errors that are incurred if we do draw the Cvs and the Cps out of those integrals, right? Because obviously we are making an error, a known error, right? By pulling the Cv and Cp out of this integral and doing Cv delta T instead of integral Cv dt, right? And so we need to understand when we can do this and why. But before we get there, we must look at how Cv and Cp change and why do they change, right? So let's look at, for example, a sample how Cp for an ideal gas changes with temperature, right? So Cv and Cp are functions of temperatures for ideal gases. So as an example, let's look at how these change. So let's plot it first for, let's say, hydrogen. This is temperature and this is Cp for Cp cap. So I'm plotting here Cp cap, right? Cp cap is Cp as units of joule per kg Kelvin, but you can imagine a Cp cap which has units of joule per mole Kelvin, right? it's easy to plot that for when you want to compare different gases. It's usually better to draw Cp cap instead of Cp because they all have different molecular weights, and so the graph might not look very easy to compare if we do a simple Cp comparison. So we are doing a Cp cap comparison, right? And so this is 20, 30, 40, 50, 60, and this is joule per mole Kelvin, all right? And this is how hydrogen looks like. Air looks somewhat like that. Air. Oxygen. For CO2, this looks very different, right? And for water vapor, again, it looks different. So as you can see, the Cp values of different gases behave very differently with temperature. So for example, if I'm working, and what is this temperature? So this is per 1000 Kelvin, 2000 Kelvin, right, and 3000 Kelvin, right? So if I'm working in this range, for example, let's say 100 to 500 degrees Celsius, 100 to 500 Kelvin, I am more or less, I can reasonably assume that the Cp value does not change with temperature. I can get away with that. Where if I'm working with oxygen or air or some such gas, right? But if I'm working with carbon dioxide, for example, I do know that the Cp value changes quite drastically in this temperature range, right? And at very low temperatures, even for air or hydrogen, I might not be able to assume that Cp is constant with temperature, right? And so if I pull this Cp out of this integral, I will be getting a bigger error, a much larger error that I want to avoid, right? So what we want to discuss in this video is why do these temperatures look, why do these Cp values change so much, and why do they change? What are these values? Why are these values the way they are? And this, by the way, is for all monoatomic gases: argon, neon, xenon, helium, etc. All monoatomic gases more or less are about 20 joule per mole Kelvin, right? And so we want to look at what Cp is and why does it change like it does with temperature, like we have shown here, right? And for understanding this, I would like you to draw an analogy, right? I try to picture that you have a bookshelf, right? And imagine that this bookshelf is quite tall, and it's quite, quite tall, much taller than you are, and obviously this bookshelf has lots of shelves, right? Lots of shelves on which you can put books in there, right? And imagine that there's an analogy between the number of books. So imagine that the number of books on that bookshelf corresponds to the internal energy U. Right? So if I ask you how many books there are, you tell me the number of books, that corresponds to the internal energy. Simple, right? And so you can imagine each book as a packet of energy, right? So if I give you a book, you get more energy to put in there. So if I give you a book to put on this bookshelf, then your bookshelf has more books, one more book, right? And therefore it has a little more internal energy than it had before, right? And the height of the highest occupied bookshelf. Let's say the book looks can we cut that part where I went out and yeah. Okay, now imagine that that you're given books to put on this bookshelf, and obviously since you're not very tall compared to the bookshelf, where would you put these books? You'd start putting them at the lowest shelves, isn't it? So you would start putting books at the lowest shelves, and once these lowest shelves are occupied, you would start putting them at the next higher shelf and so on, right? So at a given point, you might have books at all the lower shelves, let's say 1, 2, 3, 4, 5. Let's say your highest occupied shelf is the 5th shelf, right? And so the height of the highest occupied shelf is the temperature, right? So the number of books signifies the internal energy, and the height of the highest occupied shelf is the temperature, right? And so the question is then, what's the relation? If I have a large bookshelf, then the number of books that I have to give you to raise the highest occupied level is large. Whereas if you have a small bookshelf, then the number of books that I need to give you to raise the level of the highest occupied bookshelf is smaller, right? So that's the analogy that I would like you to draw. And CV takes that relationship between U and T, right? So CV is defined as the large CV, right? So is defined as dou U dou T at constant volume. Now this bookshelf, let's say, is rigid, its volume cannot change. So then I will just write it as CV equals du dt, right? So what is CV? CV is, in this analogy, CV is the number of books that I need to give you to raise the highest occupied level by 1 unit, right? So that's du dt, right? Okay. And now imagine that I have a gas, let's say argon, right? What happens if you give energy to argon? Argon will put it in the next available shelf, right? And once this shelf is full, it would move the books. It would then put new books in the 6th shelf, and then in the 7th shelf, and so on. And that's how you see that once you give more and more energy to argon, you see that the temperature keeps increasing, right? And so that's reflected in here, du dt, right? And it's more or less constant because this for argon happens to be not changing with temperature, right? Now imagine that what's this putting there? Where is this energy going? What's this kind of energy? Where is this temperature, right? It's putting all that energy in sensible internal energy. Why? Because if you give energy to argon, its molecules will move around faster, the atoms rather, will move around faster, and so therefore their sensible energy increases. And so therefore all the energy that you are giving argon is put into increasing its sensible internal energy. The chemical, the electronic and the nuclear energies of argon are not changing, right? Now imagine that instead of a rigid bookshelf, you had the capacity or the capability to expand this bookshelf a little bit so that you can stretch it a little bit, right? In a limited fashion, you cannot stretch it by an infinite amount. But let's say that instead of some kind of rigid connections, there are springs, and that you have some capacity or capability to expand these springs, right? And so what will happen is, before you put these books in higher shelves, you will try to expand the shelf and put them into lower shelves, right? Which is why the number of books that I have to give you now to raise the temperature by 1 degree Celsius, right? Or to raise the temperature by an infinitesimal amount is now larger. So I have to give you more books to raise the temperature by the same amount, right? Which is why Cp, which is dH over dt, is typically larger than Cv, right? Because you would rather expand to the extent possible this bookshelf, put those books at the lower shelves than to put them at the higher shelves, right? And so therefore, if I want you to go higher by one bookshelf, the number of books that I need to give you then is larger than the number I would have to give you if this bookshelf were a rigid bookshelf that does not change its volume, right? And so again, this temperature analogy and U analogy, I hope that you are getting it, right? Now, what happens, this is all for monoatomic gas, right? So, if we are talking about argon, helium, xenon, neon, etc. But what happens if I, instead of having a monoatomic gas, I have a diatomic gas, let us say oxygen, nitrogen, carbon monoxide, right? Then I can put these energies into different forms, right? So, for example, I can put it into rotational kinetic energy, right? Or I can put into vibrational kinetic energy, right? Which means what? In the bookshelf analogy, what that means is that I now have two more bookshelves, right? And I can put into rotational, and I can put into vibrational, and this being the translational bookshelf. So, if I give energy to argon, it has no option but to put it into translational energy because it cannot have rotational and vibrational energies, right? Because it's a monoatomic gas. But carbon monoxide, on the other hand, can put some of that energy into the rotational bookshelf and some of it into the vibrational bookshelf, right? And so, if I have levels on these bookshelves, then I would rather put these in here before I raise the level of the bookshelf. I start putting them into higher shelves, right? Now, it so happens that the gap between these two bookshelves is not the same in these three bookshelves. It so happens that the rotational bookshelf has energy levels that might look like this, right? And the vibrational might have energy levels that might look like this. Notice that these are equispaced because the energy levels or the heights of the bookshelves are separated by h nu. Why h nu? Because energy is n plus half times h nu, right? And so, between n equal to 0 and n equal to 1, I have h nu. Between n equal to 2 and n equal to 1, I still have h nu. So, which means the energy levels are equally spaced, and but this spacing is not the same as this spacing, right? And so, therefore, the Cp values keep changing with temperature, right? At very low temperatures, even carbon monoxide, even oxygen, even nitrogen can only put these books into the translational bookshelf. They do not have access to the vibrational or the rotational energies simply because those first energy levels are so high. So, imagine yourself to be that tall, right? So, you would first put these into the lower bookshelves, which are available only for the translational bookshelf. It is not available for rotational or vibrational. But as you increase your energy levels, as the temperature increases, these energy levels become accessible. And so, you can now put books into the vibrational energy levels in addition to putting them into the translational energy levels. And so, therefore, your Cp value typically increases as you increase your temperature. And when you go to still higher temperatures, some of the rotational energy levels become available. And so, some of those books which I give you are going to be put into these rotational bookshelf, which then allows you to have even higher Cp values as you increase your temperature. And when you increase it further, you can also put energy into electronic energy levels. And so, you can imagine that's a fourth bookshelf, right, in addition to all these three bookshelves that you have. And in each case, in every one of these cases, it's the same story that if I have a rigid bookshelf, then the number of books that I need to give you for 1 degree rise in temperature is smaller, whereas if the bookshelf is slightly flexible and it can be expanded, then the number of books that I need to give you for 1 degree rise in temperature is now higher than what it was if it were a rigid bookshelf, which is why, again, even for diatomic, triatomic gases, Cp values tend to be higher than Cv values, right? And so, so this is kind of a useful analogy to understand what is U, what's the temperature, and what's the relationship between Cp, U, and temperature for ideal gases, right? And remember that in these cases, we are always talking about ideal gases because we are not talking about any change in chemical, nuclear, or latent. And once we start talking about that, then you can imagine I have more and more bookshelves, right? Or you can imagine I have a multi-layer bookshelf in which to put these books, right? So you can use this analogy to understand. Now, we can derive expressions for the relationships between Cp and Cv from the definition of the enthalpy for ideal gas, definition of enthalpy, which is defined as U plus Pv, right? And we do know that for an ideal gas, that P times V can be written as RT by M, where R is the universal gas constant and M is the molecular mass of the gas, right? So I can write H equals U plus RT by M, and therefore I can also write DH equals du plus R by M dt, right? And for ideal gas, again, I know that dH it will be equal to Cp dt and du will be equal to Cv dt. So I can write this as Cp equals Cv plus RT by, getting dt out of the left and the right hand sides, I can write Cp equals Cv plus R by M, right? If I write this on a molar basis, then I can write Cp cap equals Cv cap plus R, right? And what's the value of this R? The value of this R is 8.314 joule per mole Kelvin, called the universal gas constant. And so basically you can see that R links energy to the number of moles of an ideal gas, right? And so that's pretty fundamental, right? But although it appears fundamental, it's actually a combination of two numbers that are more fundamental than, for example, R. So you might have heard of the Boltzmann constant called Kb. It's called the Boltzmann constant. It's named after an Austrian mathematician called Ludwig Boltzmann. He was the first person to link statistical mechanics and statistical thermodynamics with classical thermodynamics. So classical thermodynamics deals with quantities like enthalpy, internal energy, temperature, and we assume that these are real variables. They can have any value that we want, right? But Boltzmann argued that these can only have certain values, although in many cases the differences between these two consecutive values are so small that we assume that these are real variables. But he provided the crucial link, and we will see when we look at the second law, we will look at the link between the classical and the statistical. And at that time it was pretty controversial. Even Einstein made fun of Boltzmann, and Einstein is said to have remarked that God does not play dice. But Boltzmann showed the relationship between playing dice, playing statistical thermodynamics with those classical quantities through his relationship between what is called the entropy and the number of ways of finding a number of microstates of a system. We will not go too much into that, but so this Boltzmann constant is a pretty fundamental constant. It comes from S equals Kb log omega, and this omega, we will look at this omega later, but this is the Boltzmann constant, and so this is an integer. This can only have integer numbers. It's a very large number typically, but it's a finite number, and Kb links this finite number, which can only be an integer, which means the energy levels can only be discrete, with this variable entropy, which we normally work with, and we treat it as if it's a real and continuous variable, right? So it's a pretty fundamental quantity, and its value, so 1.38 10 to the negative 23. This is per mole. This is joule per Kelvin, right? I was confusing with the Planck's constant. Yeah. So when you multiply Kb with Na, you get R. So is Kb multiplied by Na, so that is equal to 8.314 joule per mole Kelvin, right? So it's linked to that. It's not necessary for you to know this at this point, but it's just good to know that this R is a universal gas constant, but it actually comes from Boltzmann constant, which is 1.38 times 10 to the negative 3 joule per Kelvin, and the multiplication of that number with the Avogadro number here. Okay. Anyway, back to where we were. So in some cases, we can approximate Cv and Cp as a constant, in which case we can pull it out of the integral and do the simple difference of temperatures times the constant Cp or Cv, but in many cases we cannot, and for those cases we need to do approximations, and some of those approximations are also given in your textbook. I will not go too much into detail, because most of the time we will now be using computer programs that are capable of producing very accurate results, because this integration has already been done for you.